Hi everyone, this is the first video for Unit 2, and we are moving on to carbonyl chemistry. Particularly the class of molecules we're going to look at are ketones and aldehydes. And in this illustration, what I'm showing here is the polarity of the carbonyl bond. The carbon-oxygen bond is called the carbonyl bond. And I'm looking at the picture on the right, where oxygen is partial negative, which renders this carbon partial positive. When this carbon is partial positive, it can attract a nucleophile. And that's going to dictate a lot of the reactions we are going to see in future videos in this unit. Over here, this is an illustration of the electrostatic surface potential map of carbonyl, and dark blue areas are going to be electron poor, and red areas are going to be electron rich. But why don't we start from the beginning, which is what is a ketone and what is an aldehyde? So let me just draw you a couple of examples, and we're going to start with the ketones. The ketone is a molecule that has a carbonyl group, and again, the carbonyl group is literally the carbon-oxygen double bond, and that's the functional group. So Fg functional group is called the carbonyl, and I'll put a dotted circle around it. The thing with ketones is that on each side of the carbonyl group you have a carbon. Okay. In contrast, aldehydes, I'll do it next door. Aldehydes have at least one hydrogen off of the carbonyl carbon. And one example, well, not example, but this is a general picture of an aldehyde. And again, you are going to be focusing on the carbonyl group, but if there's a hydrogen on at least one side, then you have an aldehyde. What are some ways that we can represent, what are some drawings we could use to represent these classes of molecules? So here's a line drawing of a ketone. How about a line drawing of an aldehyde? Well, for an aldehyde, the carbonyl group is at the end of the molecule, and a lot of people don't draw the hydrogen here, but out of habit, I like to draw the hydrogen here, but it's unnecessary. But I just like the idea that we put a little cap here. Ketones and aldehydes. With the ketones, you want to be a little bit careful with the condensed structure. You may see something like this in literature. In Unit 1, we had just gone over ethers, and one may think that this is an ether, where you have an oxygen singly bonded to two carbons. But the fact that this carbon has no hydrogen means that we're going to have to put a double bond to this oxygen to make sure that this carbon is tetravalent. So for this condensed structure, the line structure is actually this. And you could number your carbons and just double check. 1, 2, 3, 4, 5. And you notice again that this carbon in the center has no hydrogens, and same thing here for this carbonyl group, no hydrogens on that carbon. For the aldehyde, there are other ways to represent an aldehyde, and one way to do that is to use condensed structure to represent the carbonyl group. And in this case, well, for all aldehydes, you could abbreviate the end as CHO. Just be sure if you're going to do that you have the right number of carbons. 1, 2, 3, 4. 1, 2, 3, and 4. Okay, so that is structure. What else can we say about this? Well, as long as we have this drawing, you remember what the orbitals are combining or overlapping to make this carbonyl group. You have a sigma bond between a carbon that's what? A carbon that's sp2 and an oxygen that's sp2. Then we have a double bond, right? So we have a pi bond. We can't have two single bonds, or we can't have two sigma bonds. We have a pi bond, and that's almost always between two p orbitals. So those are the orbitals that are overlapping to make this carbonyl group. I'm not going to draw the cartoon where we have lobes. We could save that for a later time. What I do want to do is move on from structure and talk about nomenclature, the naming of ketones and aldehydes. Well, before we get to the IUPAC naming, there are some ketones and aldehydes whose common names are used rather than IUPAC naming. And here we have that is the simplest ketone. That is called acetone. That's the common name. Now we're going to move on to the aldehydes. Now, if your carbonyl group has a hydrogen on each side, that is formaldehyde. If you have only one hydrogen on one side and you have a methyl group on the other, I might have mentioned this in Unit 1. This is acetaldehyde. Why would I have mentioned this in Unit 1? Because ethanol, drinking alcohol, is metabolized to acetaldehyde, and this is commonly known as the hangover drug. This is the compound that does give you a hangover the morning after drinking a lot of ethanol. The last common name, and I don't expect people to memorize the structure, but a lot of aldehydes are involved with flavorings, scents, how things taste, essential oils, and this is an aldehyde called cinnamaldehyde. Cinnamaldehyde. Obviously, a compound that's found in cinnamon. Why don't we move on to IUPAC naming? And the first molecule that I want to look at is this. If you want to catch up or make sure you have this correctly drawn, go ahead and pause the video. The rules are very analogous to what we've seen before. Number 1, find the longest carbon chain. But, with alcohols, we needed to include the alpha carbon. We need to include the carbon, in this case, of the carbonyl group. Technically, this is not called the alpha carbon anymore. Don't worry about it. Just remember that you have to include in the longest carbon chain the carbon of the carbonyl. All right, and in our case, the longest carbon chain is not 1, 2, 3, 4, 5, 6, 7, because I didn't include this carbon, so that can't be my parent. We're looking for the parent. It is actually this one. 1, 2, 3, 4, 5, 6. So our longest carbon chain has 7 carbons, but it's not the parent because it did not include this dot. To include this dot, we'd have 6 carbons in a row. And then you go to number from the end closest to carbonyl. Now, is a carbonyl group, does it have precedence over other groups? Yes. You want to number from the end closest to carbonyl over other groups such as halogens and alkyl groups. Now, probably a question that some of you have is, well, what about hydroxyl groups? And that's a good question. Let me just double check. I actually don't have a good example of that. Oh man, let me look up real quickly. I'm going to pause the video. I'm going to look up, and we are going to name molecules that have a carbonyl group and a hydroxyl group. Okay, so let me just, I'll pause the video and I'll be right back. Okay, we're back. I looked it up, and the carbonyl group takes precedence over halogens, alkyl groups, and hydroxyl groups. Let me wipe this out. Carbonyl beats all of them. And we'll do one example with a hydroxyl group and a carbonyl group next. But let us finish this. We're going to number it from this end here. 1, 2, 3, 4, 5, 6. And we have a group on the carbon number 3, the propyl group. 3 propyl. Now we do have to locate where the carbonyl group is along the chain, and it's at the 2 position. This is 2. Instead of hexane, we get rid of the E and add O and E. Hexanone. And again, this 2 tells you where the ketone is, or the carbonyl group of the ketone is. And obviously we have our substituent. So let me put that as the third rule. You drop the E and you add O and E. Instead of saying hexane, you have hexanone. Okay. Now, where was the example that I was tripping all over the place with? I would have tripped over trying to name this molecule here. But now, after I've seen the rules, let us tackle this. Knowing that the carbonyl group has precedence over the halogens, alkyl groups, and hydroxyl groups, we are going to number this chain from the left. And let me put a dot here. It's just out of habit. So our carbonyl group is on carbon number 2 of a 4-carbon chain, so that's bute. But what do we do with this hydroxyl group? The hydroxyl group is a substituent. And when the hydroxyl group is a substituent, rather than the functional group that's going to dictate what the parent is called, right? The parent has to be, because carbonyls take precedence, the parent has to end in O and E. It cannot end in OL. So when the hydroxyl group now becomes out of the parent and becomes a substituent, we're going to call this a hydroxy group. Okay? I know it's a lot of rules to remember, but it would be good to remember, since we went over alcohols, we may run into molecules now that have a combination of a hydroxyl and a carbonyl, but when we name it, we're going to call it hydroxy. So it's a hydroxy group. And the name for this one is 4 hydroxy dash 2 butanone. Or we saw this with alcohols. Some textbooks are now putting, and it's acceptable, putting the number as close to the suffix as possible. 4 hydroxy, and you may see something like this: 4 hydroxy butan 2 O. All right, let's remember these rules because we are going to now work with aldehydes, which have also a carbonyl group. But the thing with aldehydes is that the carbonyl group is at the end because there has to be at least one hydrogen attached to the carbonyl carbon. And let me give us an example. How about this one? For an aldehyde, and we know it's an aldehyde, right? Uh, the aldehyde carbon or the carbonyl carbon is automatically number one. No matter what you have on the rest of the chain. You could have bromines, you could have chlorines, you could even have a hydroxyl group. This is always carbon number one. And since that is the case, you will never have to say that the carbonyl is on carbon number one. So we're not going to write number one. For a ketone, you have to tell the reader where the carbonyl group is. But here, it's automatically number one, so it's redundant. If you have an aldehyde, that is carbon number one. And we're going to call this 3-bromo, 5-methyl. It's a 6-carbon chain, so it's hexane. We remove the E, and I haven't told you this yet. You add Al. Hexanal. For your grader, you need to draw, or you need to write very, very legibly because you can't afford to have your grader think this is an O. If it's hexanol, it announces that you think this is an alcohol. But it's hexanal, it is a aldehyde. No space. And also no number one. Alright. I won't name this here, but again, just remember it has to include the carbon of the carbonyl group, okay? And we'll name this together actually. So our longest chain, that's the parent, is not 6. It's not 1, 2, 3, 4, 5, 6. Because I never included what? The carbon of the carbonyl. Number 1 has to be that carbon. 2, 3, 4, 5. This OH group would normally make the molecule an alcohol, but since the carbonyl takes precedence, we're going to call this a hydroxy group. And then our other substituent is this one right here. Alphabetize 2-ethyl, 4-hydroxy. 5 is pentane. You remove the E and you add Al. 5-hydroxy, 4-hydroxy, pentane. Now, one more name and then we can move on. What if we have a benzene ring and we have a carbonyl group hanging off of it and it's an aldehyde? The acceptable IUPAC name here is benzaldehyde. Okay, so it does come from the word benzene, and it is an aldehyde. And this is acceptable. This is the IUPAC name. Okay, benzaldehyde. And then when we start putting substituents, for instance, we put a methyl group right here. This is carbon number 1 automatically. So this will be, if there's a methyl group here, we have 3-methyl benzaldehyde. We'll talk more about molecules that have benzene much later in the course, but that's as far as I want to go with naming for nomenclature. Let's take a look at polarity real quickly, because I do want, and I'm hoping I do get to some synthesis. This will be a review, so this will go a little bit fast. But real quickly, the polarity, and we did mention it at the beginning, where your bond is a pretty polar bond actually. It's a fairly large dipole, and here we have it indicated with a dipole arrow, indicated with electrostatic potential map, indicated with partial charges. Okay. And honestly, I'm not going to draw this under my doc cam. Why don't you go ahead and copy this one right here? Because what this is saying is that due to the dipole of the carbonyl bond, we could have very interesting chemistry. That carbon is attractive to a nucleophile, which is electron rich, right? Nucleophiles are electron rich and they attack electron poor. Not only that, this oxygen is basic, so maybe even before the nucleophile attacks, this oxygen is protonated. It just depends, and we'll go through plenty of examples slowly. It just depends whether you're under acidic conditions or not, whether you want to protonate first or if you want the nucleophile to attack first in terms of looking at the mechanism. Okay? And this bears out in calculations, this bears out in experiments, that this carbon right here is the one that's attracting the nucleophile and the one that's going to be attacked. There is one thing that I do want to draw, and then we can move on to some properties. The one thing I do want to draw is that there is an acceptable resonance structure for a carbonyl group, and it's this one right here. Now, you might think that this is a little bit weird because, well, it's not a very major contributing structure because we have we have separation of charge. Also, we have a carbon that doesn't fit the octet rule. It's still a resonance structure, though. Okay, it's just a very minor one. So this is a resonance. But this is the major contributor, obviously. Hopefully it's obvious. But what does this tell us? If the actual molecule is the combination of your two resonance contributors, then yeah, this carbon does have a significant positive charge. Not a full positive, but a partial positive. Somewhere in between what? Somewhere in between neutral and +1. And because of this resonance is acceptable, and it is true, that carbon is fairly partial positive, fairly electron poor. Now, yeah, I have time. This is going to be a review. We are going to review fairly quickly how to make ketones and aldehydes. Ketones and aldehydes. From organic 1, what did we look at? We looked at, oh yeah, we looked at ozonolysis. So, for instance, if I have this molecule here, this is not a common way to try to make a ketone or aldehyde, but let me show you the example though. Ozonolysis, you have ozone, and typically the second reaction could be dimethyl sulfide or zinc and water, but I just memorize dimethyl sulfide. Ozone for ozonolysis. What you want to do is you want to cut the double bond. Go ahead and put your 2 dots. I like to put 2 dots because those are the dots of the carbonyl. Those are the carbons of the carbonyl. So we have this dot. Oh, I didn't mean to do this. We have 2 aldehydes. You see why we actually have 2 aldehydes? When we separate the 2 pieces after we make the cut, both of these carbons have a hydrogen on them. So we did end up with 2 aldehydes. If I wanted a ketone, what could I have done? I could have put in a methyl group right here, right? And then this would have been a ketone. No big deal, right? But here's your one way to make carbonyl compounds, right? Ozonolysis. The other way, very, very recently, in Unit 1, we could do oxidation. So let's take a primary alcohol. And we can't oxidize it all the way to the carboxylic acid because I want to make a ketone or aldehyde. I'm going to use PCC. This is review from Unit 1. And my aldehyde looks like this. Okay. You can't use chromic acid or Jones oxidation because you'll bypass the aldehyde and make the carboxylic acid. We have here aldehyde. Now, we could make ketone if we take a secondary alcohol, and yeah, we can use chromic acid. More popular than just straight up chromic acid is this combination, potassium chromate and sulfuric acid, which makes chromic acid in the reaction flask, and you will get the ketone. Or, don't forget that you could also use PCC. PCC is special in the sense that if you have a primary alcohol, you won't get the carboxylic acid. But for the secondary alcohols, you could get the ketone either way, Jones oxidation or PCC. All right, so that's two ways so far. We have ozonolysis from organic chemistry 1, and here we have oxidation of alcohols from unit 1. For my class, this is organic chemistry 2. There actually is one more from organic chemistry 1 to make aldehydes and ketones, and it's a very slick way to do it. It's through a terminal alkyne. For my class, anything that is review is fair game for the exam, even if it's organic 1. So you'll need to, make flashcards, and if you think you're going to forget a very important organic 1 reaction, make a list. Make a list of organic chemistry 1 reactions that you know you're responsible for, and you are responsible for it if I go over it. The last one is alkynes, hydration of alkynes, terminal alkynes. And let's give an example right there. I'm going to put my 2 dots. Remember this reaction where you could do hydration, acid catalyze in one sense or one case? When you do acid catalyzed hydration of an alkyne, typically you do want this mercury 2 sulfate, it's a +2 charge, and you're going to put the carbonyl on the more substituted carbon of the alkyne, or the triple bond, and you go from a triple bond to a single bond. Does that look familiar? The other reaction will go down this way, is the borohydride, the hydroboration oxidation. But there's also a special reaction here when you start with alkynes, SiA2BH. Those are just alkyl groups to make it a little bit more bulky, a little more selective. Put the oxygen on the last carbon, not this carbon here. H2O2 NaOH, and we have this dot carbonyl. Okay. The difference here is that for the first reaction, we put the C double bond oxygen on this carbon, and then for the second reaction, we put it on, on this carbon right here. Okay. That is all I want to talk about. Okay, and those are the 3 ways that you're going to form carbonyl compounds, aldehydes, and ketones. The rest of the videos in this unit are going to be a list of reactions, and I will go over the mechanisms that I would want my students to know. But for for many reactions in this unit, we won't need to, or I won't show you the mechanism. It will be mainly filling the product.